These are examples for section 10.4, angles of elevation and depression. From the trigonometry lesson we had, this is an extension lesson from that. Angles of elevation and depression are used many times in trigonometry using the sine, cosine, and tangent ratios. So, knowing what these two angles are, let's apply what they are. Take a look at an example of describing these kinds of angles. Example 1. What is a description of the angle as it relates to the situation shown? Here we have a balloon, a boy in the balloon, and a bird, a mountain, and this is sea level right here. And we've got various angles going on here. And recalling the definition of these two types of angles, part A, angle 1, right here, whether it's an angle of elevation or depression, how do we know which is which? The angle of depression, this is an angle of depression, and we know that because the vertex, starting at the vertex of the angle, there is a horizontal line is one of its sides of the angle, and then the other side is below that horizontal line. So that's how we know this is an angle of depression. Now, it's an angle of depression from where the first ray is pointing to, which is the top of the balloon, from the top of the balloon to where it extends downward to the boy in the balloon. So, angle 1 is an angle of depression starting at the bird from the top of the balloon to the boy in the balloon. Angle of depression. Part B, angle 4, this angle right here, its vertex is at the base of the mountain. It's an angle of elevation because the ray that's horizontal, from that ray that's horizontal on that angle, there's another ray that's above that ray. So this is how we know it's an angle of elevation. It pushes upward. So it's an angle of elevation from sea level to the boy in the balloon. So once again, angle 4 is an angle of elevation from sea level to the boy in the balloon, going upward. Now it's your turn to try to describe a couple of angles. Practice 1. What is a description of the angle as it relates to the situation shown? Same situation, mountain, balloon, bird, and sea level. This time A and B. Go ahead and do A and B. Pause the video, come back, and turn it back on when you're ready. Okay, practice 1. Part A, angle 2. Angle 2 is an angle of elevation because the horizontal line, from that horizontal line, part of the angle, it moves upward to an object above that. So it's an angle of elevation from the top of the mountain to the bird. Angle 2 is an angle of elevation from the top of the mountain up to the bird. Part B, angle 3. This one right here. Angle 3 is an angle of depression. It's an angle of depression because it's horizontal. From its horizontal side, it moves downward to an object below from the line of sight. So the vertex is at the boy, and it goes, the angle of depression for angle 3 goes from the top of the mountain to downward to the base of the mountain. Or sea level. Example 2. Suppose a building is located 400 feet from a wind farm turbine. Building, wind farm turbine, 400 feet. A worker is standing at a window on the second floor of the building, right here. The angle of elevation to the hub of the turbine is 35.5 degrees. So the angle of elevation from here, line of sight, upward to the hub, that's the center of the wind farm turbine, is 35.5 degrees. The worker's eye level is about, or is 15 feet above ground. So from here down is 15 feet down to the ground, right here. Approximately how tall is the turbine from the ground to its hub? So what we're looking for is clear from the ground all the way up to the hub there. So our strategy is to find the length or distance from all the way down here all the way up to the hub. Well, we've already got 15 feet of it, so we're going to need to add 15. And then from there all the way up to the hub, we need to find that length x. So what we really need is x plus 15. That's what we're looking for, x plus 15 feet. When we start this, we notice we have a right triangle formed by this line of sight and this angle of elevation. And so this right triangle, trying to determine which trig ratio to use, of course we're going to use this angle. And so we're looking for its opposite side, and we have its adjacent side. So this would be the tangent. So the tangent of the angle of elevation, 35.5 degrees, is equal to opposite, which is x, over adjacent, which is 400. Now we solve for x. Since x is divided by 400, we multiply both sides by 400. Those divide out, and we're left with x equals 400 times the tangent of 35.5 degrees. Take your calculator, calculate 400, make sure you're in degrees mode. 400 times tangent of 35.5 degrees, and we're going to round to the nearest foot, and that'll give us about 285 feet. So 285 feet is from here all the way down to that line of sight. Now all we need to do is add the 15 feet. So we take this, and we have x, which is 285 feet, plus 15 more feet, and this gives us the height of that windmill. And that gives us about 300 feet. Once you start approximating right here, then everything subsequent to that is approximation too. So anyway, it's 300 feet tall from the ground all the way up to the hub. Example 3. To approach runway 17 of the Ponca City Municipal Airport in Oklahoma, the pilot must begin at a 3% or 3-degree descent starting from a height of 2,714 feet above sea level. The airport is 1,007 feet above sea level. To the nearest tenth of a mile, how far from the runway is the airplane at the start of this approach? First of all, they're asking for the how far from the runway the airplane is. So that would be this distance right here. So this is what they're asking for, not this distance. This would be the land distance. So I'm going to write D for distance right here. Notice we have the line of sight, horizontal line, always horizontal with the horizon. and this is an angle of depression, 3 degrees. Well, don't seem to have a triangle anywhere. However, it did say that the airport was how many feet above sea level? 1,007 feet above sea level. So obviously sea level's below somewhere. I'll just draw a line down here somewhere. This is sea level. And from here up to the airport, this distance right here, I'll just put it right here, is 1,007 feet. Okay. Well, that means it's 1,007 feet directly below the airplane too. So from here to here is also 1,007 feet. It also mentioned that when they make the descent, they're at a height of 2,714 feet above sea level. So the airplane here, this whole distance from the airplane all the way down to sea level is 2,714 feet. Already you can see a triangle forming. The altitude of the airplane, we assume, is perpendicular to the ground. We always do that. So here we have a right triangle. Now the problem is we don't have one of the two acute angles, but we do have this angle of depression or angle of descent from the airplane here. So how can we find out one of these other two acute angles from it? There's two different ways you can do it. You can use complementary angles. You know this is a right angle and you can find this angle. Or I think something that's a little simpler is to notice that this horizontal line is parallel to the horizon line or the ground line. So these are parallel, and therefore this angle here has to be congruent to this angle here by the alternate interior angles theorem. So this also has to be 3 degrees. Now that we have this angle, we've got one of the acute angles in the right triangle. We don't directly have the length of this side of the triangle, but we can find it pretty easily by using segment addition, taking this entire segment from the airplane down to sea level and subtracting out the distance or height between the sea level and the ground. We can find what this is right here. So this is the difference of these two. So I'm going to write 2,714 minus 1,007 feet. That's from here to there. Now we have enough information to find D. Now we try to figure out which trig ratio to use. We're using this angle here in the triangle. I'm going to go ahead and redraw the triangle because it's getting quite complicated looking. So I'm going to redraw the triangle that we're using. And I've got this side, which is 2,714 minus 1,007 feet right here. This is the right angle. This is 3 degrees, and we're looking for the distance between the airplane and the runway of the airport, so that's D. Now you can clearly, or more clearly, see what we're doing here. This angle right here, that would be the hypotenuse, has to be included, and the opposite side. So opposite and hypotenuse, that's sine. So we take the sine of the angle 3 degrees, and it's equal to the opposite side, which is 2,714 minus 1,007, over what we're looking for, the hypotenuse, D. So there's an equation that we would use to find part of our answer here. Just to keep in mind, everything we've been doing has been in feet, but they're asking for miles, so we'll have to remember that at the very end. Okay, so let me solve this. Sine of 3 degrees is equal to, when you subtract 2,714 minus 1,007, you get 1,707 over D. Now to solve for D, we multiply both sides by D to get rid of D in the denominator. Those divide out, and now we have D up here in the numerator. So this is D times the sine of 3 degrees equals 1,707. One more step to solve for D. We need to, since D is multiplied with the sine of 3 degrees, we divide both sides by sine of 3 degrees. Those divide out, and D is equal to 1,707 over sine of 3 degrees. Now, to approximate that, we put in our calculator, make sure it's in degrees, 1707 divided by the sine of 3, close parenthesis, and we get approximately 32,616 feet. Now, there's a lot of feet in 1 mile, so we're going to just round to the nearest foot, nearest one's place. So this is about this many feet. We want to know how far it is in miles. Well, we just found this in feet, 32,616 feet. Now, to find in miles, what we need to do is convert. Use a little dimensional analysis, or conversion analysis here. So we have 32,616 feet, and we need to multiply it by a conversion factor using miles and feet. And so if you don't remember, there are 5,280 feet in every mile. So this is something you would either have to be given or look up or have to be able to finish this problem. So right here, we want feet to cancel out. So I put feet down here. That means miles are going to be up here because that's what I want. We want these to divide out. Well, there again are 5,280 feet in 1 mile. So when we multiply this conversion factor with this, we get 32,616 times 1 mile, which is 32,616 miles, over 1 times 5,280 is 5,280. Notice the feet are gone now, but the miles are still there. And then now we just simply take 32,616 and divide by 5,280, and that will give us an approximation in miles. So dividing those out, and we're going to round it said to the nearest tenth of a mile. So when we do that in our calculator, we get 6.2 miles. So it's going to take 6.2 miles for the plane to reach the runway. Example 4. A firefighter on the ground sees a fire break out through a window near the top of the building. Right here. Yeah, she looks up at it right there. The angle of elevation to the windowsill is 28 degrees. So the angle of elevation from where she sees, this line right here, up to the windowsill for where the fire is on the second floor is 28 degrees right here. So there's a right triangle formed with this horizontal line and the line of sight and the building. So there's one right triangle. The firefighter is 75 feet from the building. So that's where this is. That means this is 75 also. And her eyes are 5 feet above the ground. So her eye level is 5 feet above the ground. So from here down to here is 5 feet. What roof to windowsill distance? So roof right up here to windowsill distance where the fire is. So they're asking for what the distance from roof to windowsill, what this is right here. We'll call it D for distance. Can she report by radio to firefighters that are on the roof? Maybe they need to know how far down they need to drop a firefighter to the windowsill. Well, this just created another. When she looks up at the roof, it creates another right triangle, and it's overlapping the first right triangle. So here's the first one. And so we're going to need to find this. Of course, we need to know how far up from there to the windowsill. So this is going to be, well, let's call this Y. This distance right here. So this right triangle, this is Y. But we also are dealing with this right triangle here, which has a 42 degree angle of elevation to the top of the building. So we're also dealing with this entire length here, which is, we'll call it X. So if we're wanting to know how far it is from the roof down to the windowsill, we need this length right here To find it, we're going to have to take this entire distance, x, and subtract off this distance, y, using segment addition postulate. Before we can do that, though, we're going to need to know how long this is, x, and how long y is, so that we can subtract them. So eventually, we're going to take x and subtract y, and that's going to be how many feet that she can report to the firefighters on the roof. That'll give us D. So to do that, we need to use trigonometry. So the first one, let's call this up to the windowsill. So to the window. And then over here, we'll figure out the triangle that's the triangle all the way up to the roof. To the roof. Okay, so one thing before we continue is anytime you're working with approximations, it's always best to keep from approximating as long as possible during the problem, because if you approximate too soon, then as you start operating on that answer that's been approximated, it shoots that answer further and further off the actual amount. So we're going to try to keep everything exact as long as we possibly can. I'm going to show you how to do that on this problem. Okay, so to the window, this triangle right here, we've got the angle right here from the firefighter, angle of elevation up to the seal, and we're looking for the opposite side, and we're given the adjacent side right here, 75 feet. So we're going to use the tangent. We're going to find the tangent of 28 degrees is going to equal opposite, which is y, we called it y, over the adjacent, which is 75. And we'll get back to this in a moment. The triangle that goes up to the roof, we're going to do the same thing. We've got this angle here, 42, and opposite that angle is x, this length right here. So this would be the tangent of 42 degrees, the same trig ratio, because we still have opposite over adjacent, equals x, opposite over adjacent, which is the same side right here, 75. Okay, we solve each equation. We need to multiply both sides here by 75, and we get 75 times the tangent of 28 degrees equals, those divide out, we get y. Now let's not do anything with that yet. Let's come over here and solve this one. Again, multiply both sides by 75. And so these divide out, and x is equal to 75 times the tangent of 42 degrees. Now, as I said before, but before approximating these, if we approximate them now and then later we subtract them, it's going to shoot the answer further and further off of its actual value. So instead of doing that, we're going to keep these in this form and put it in this form. So our distance that we're looking for is equal to the difference between these two. So x was 75 times the tangent of 42 degrees minus y, which is 75 times the tangent of 28 degrees. Now one thing we can do here, since this is 75 tangent 42 degrees and 75 tangent 28 degrees, 75 is a common factor in both of these, so we can factor out of 75. So I factor out of 75, and I have left tangent of 42 degrees minus tangent of 28 degrees. These aren't the same because they have different angle measures. Now that's about as far as we can go. So now we take our calculator, and we are going to find an approximation now. So what you do is you put in 75, make sure you're in degrees, open parenthesis, tangent, and it already opens another parenthesis when you do that, so account for that. 42, close the inner parenthesis, minus tangent, it opens another set of parentheses, 28, close that inner parenthesis, and now we have to close the outer parenthesis. Enter. And we get about 27.65209595, so forth. And we're rounding to, let's see, the nearest foot, I believe. So the distance, I would want to be pretty accurate if I were telling firefighters how far down to go. So I'm going to round to the nearest tenth of a foot. So that would be 27.65 That pushes that up to 7 feet. So this is how many feet, pretty close to how many feet the firefighters are going to have to move downward from the roof of the building down to the sill of the window on the second floor. And did you notice we did not use the 5 feet above the ground? This was some extraneous information that we didn't need. Sometimes that happens, so be aware of that. Example 5. A blimp provides aerial television views of a football game. Here's the blimp right here. The television camera sights the stadium, and of course the camera crew is right up here in the blimp. They sight the stadium at a 7-degree angle of depression. So the horizontal line coming out from the blimp, its line of flight there, going down 7 degrees, they see the base of the stadium here. And so what is a line of the blimp is 400 meters high above. So here's the altitude right here, the blimp. What is the line of sight distance? The line of sight distance from the television camera to the base of the stadium. So right here, we're looking for this. So I'll call that D for distance. Round to the nearest 100 meters, not hundredths, but 100 meters. See if you can do this one on your own. It's fairly similar to the problem we did dealing with example 4 and a little bit like example 3. Pause the video and then turn it back on when you're ready. Okay, in example 5, first of all, this is a lot like the other one we did with the airplane. You've got this horizontal line here, and you've got the ground line here. Well, these are parallel because horizontal lines are always parallel to the horizon, which is the ground line. So this is an alternate interior angle with this one, and so we can create a triangle here in which this is 3 degrees. Because alternate interior angle, 7 degrees. These are alternate interior angles, so these are both 7 degrees. So alternate interior angles theorem, and I'll write 3 degrees in parentheses, 7 degrees. Okay, and so I'm going to go ahead and redraw the triangle so it's just easier for us to see. And so we have, let me do it over here. And there's the stadium. Here's the blimp. Here's the camera television crew. Here's D. Here's the right angle. This is 400. And this is 7 degrees. Okay, we have everything we need if we want to find this length, because we have this angle and we have at least one of the other 3 sides. So we have this angle right here. This is an opposite side. So we need opposite. We also need the hypotenuse. So that would be sine, cosine, or tangent. Sine. So sine of 7 degrees is equal to opposite 400 over hypotenuse D. Solve for D. Multiply both sides by D. Those D's divide out, and we get 400 on the right side, and D times the sine of 7 degrees on the left side. Now we need to divide both sides by the sine of 7 degrees. The sine of 7 degrees divide out here, and D is equal to 400 over the sine of 7 degrees. That's the actual, literal, exact distance from the camera crew down to the base of the stadium. Okay, well, we need an approximation as usual. So we take our calculator and we put in 400, make sure you're in degree mode, 400 divided by the sine of 7 degrees, close parenthesis, and you're going to get, actually you get 3,282.204, so forth. But they wanted us to round to the nearest 100 meters, and so that would be, this is the hundreds place, So we look at the next place. This is 8. It's going to push this one up 1, and then these become zeros, and we need those zeros because they're before the decimal point. And then all these become zeros. So we have 3,300 meters. So about 3,300 meters or 3,300 meters from the television crew down to the base of the stadium. There is another way to do this problem using cosine. We could have used this angle right here and used complementary angles and angle addition. We would have said this is a 90-degree angle, and 90 minus 7 gives us 93 degrees. So we would take the cosine of 83, not 93, 83 degrees equals, and then cosine would be, we'd have this angle here, cosine would be adjacent, which is 400, over hypotenuse, d. So you would have solved this one, and you're going to get the same answer. So this is an alternative way to do it. Example 6. A communications tower is located on a plot of flat land. The tower is supported by several guy wires. So here are the guy wires, here and here. Assume that you are able to measure distances along the ground, so we can measure any distance along here that we want to, as well as angles formed by the guy wires and the ground. So all the angles that connect the ground to the guy wires. So any of these angles here and here. These are all, think about it in a practical way. We can measure these since they're on the ground by just walking around. It would be hard to measure some of these angles up here or figure out distances because we'd have to go up in the air. So this is a pretty practical problem. Explain how you'd find each of the following measurements. A, the length of any guy wire. So we're going to see if we can find the length of any one of these guy wires. And B, how high on the tower each wire is attached. We also want to find out how high any one of these guy wires are attached to the building. Well, to do this, to find a way to do it, we need to at least take one example dealing with one guy wire. I'm just going to take this one right here. I could take any example I wanted to, any guy wire I wanted to in the tower. But anyway, there's that right triangle. And so we assume that's a right angle because the tower is being built at perpendicular to the ground. And if I want to find out the length of any guy wire, this would be our guy wire here. So I'll call it, how about X? This would be my guy wire, and of course this would be the length up to where it attaches. That'll be part B. But we also could find this out here too, because we can walk off that distance. They said we could find any one of these ground distances. So I'm going to call this D for distance. Alright, then they told us that we can figure out any angle that connects a guy wire to the ground. So this angle right here would be the angle we would use. Not this one because it's way up on the tower. So using this angle here, I'm going to call this A degrees. Just use any letter you want to. I'm going to use A. And to find out the length of this guy wire, I would have to use a trig ratio. Well, which trig ratio would that be? Because it said, explain how you would find each of the following measurements, the length of any guy wire. So the length of this guy wire using this angle and this side, we would have to use which trig ratio? This is adjacent to this angle, and this is the hypotenuse. So our part A, the first part of the answer, is you would use the cosine ratio. Now here it says write a formula that could be used to find any guy wire length using variables suitable for the situation. So we're going to need to find a formula that will allow us to do that. Well, we would just set up our cosine situation here with the one we just drew. So the cosine of the angle A degrees is equal to the adjacent side D over the hypotenuse X. And then we would write comma solve for X, because that's what we would be looking for. So we go ahead and solve for X, even though there's no numbers in here. We go ahead and solve anyway. We take cosine of A degrees equals D over X. We need to get X by itself. Since it's in the denominator, we need to multiply it to get it out of the denominator. Those divide out, but we have to multiply by x over here. So now x is in the numerator. X cosine a degrees is equal to d now. We still need to get rid of the cosine a degrees. X is being multiplied with it, so we divide both sides by cosine a degrees. Those divide out, and here's the formula that you would use to find the length of any one of these guy wires. Depending on which guy wire would depend on how long the D was. We use this triangle here, we could use this triangle, or any of these other three. So this is the formula we would use to find any guy wire length. So here's your first answer, here's your second answer. Part B, they just want us to find how high on the tower each wire is attached. So I'm going to take this, let's just take another triangle. Well, let's take the same one. Take this triangle here. Draw it. Here's the guy wire. Here's the ground. Here's the tower right here. Okay, if we're going to try to find any of the where these are attached, where this is attached, we need to know this height right here. So we want to know where the guy wire is attached there, or if you took this triangle, you would want to know where the guy wire is attached there or there. So just as an example, this middle one here, how high that would be. So this right here would be a new variable, y. And so again, we've got the angles along the ground with the guy wire, so we'd have to use this angle here, and then we can measure the ground line here, so we'd have this as D. So once again, I'm going to use a degrees again. This would be which trig ratio? How would we find that? We've got this angle, we've got an adjacent side, and we've got the opposite side. We would use the tangent ratio. Okay, it didn't ask us to find a formula for that, but if you did, you could set it up like this. The tangent of the angle is equal to opposite y over d, the distance, and you'd solve for y. To solve for y, you multiply both sides by d, and get d times the tangent of a degrees equals y. And that would be your other answer. You take the distance of that ground distance times the tangent of the angle there, and that would give you how high that guy wire connects.